In this presentation, I will be explaining the performance of FM radio receivers. Let us look at the block diagram of a FM radio receiver. The first block in every radio receiver is a band pass filter which selects the desired station, rejecting all other frequencies. Mainly, it has a tuned circuit for this purpose. This is then followed by the limiter, which limits the amplitude of the FM signal to a constant value. Here we are interested only in the frequency variations or the angle variations. The discriminator demodulates the signal. The low pass filter selects the desired frequencies, rejecting all other unwanted terms. The modulated signal is a FM signal, which is given by the expression S of t equal to AC cos 2 pi fct plus 2 pi kf integration of m of t dt. FM will have a bandwidth of bt hertz as given by the Carson's rule. The band pass filter will have the same bandwidth as that of the FM signal, because the band pass filter has to allow FM signal having a bandwidth of bt hertz. Since the bandwidth will be much smaller than the carrier frequency Fc, the noise at the output of the band pass filter is called the narrowband noise. The limiter limits the amplitude to a constant level if any spurious amplitude variations are present. The discriminator demodulates the signal followed by the low pass filter. Now, let us look at the noise at the output of the band pass filter. It is a narrowband noise given by the expression n of t is ni of t cos minus nq of t sin. This can also be expressed in terms of the magnitude and the phase by n of t is equal to r of t cos 2 pi fct plus psi of t, where r of t represents the magnitude of the narrowband noise and psi of t represents the angle with respect to cos 2 pi fct. The band pass filtered output is a FM signal plus the narrowband noise. FM signal is given by AC cos 2 pi fct plus phi of t, and the narrowband noise is r of t cos 2 pi fct plus psi of t. Now, let us evaluate the angle of the resultant vector. From that angle, we will take a frequency variations. In order to find out the angle, let us represent the signal x of t vectorially. The first part is a signal, that is AC cos 2 pi fct plus phi of t. It is represented by AC vector of larger magnitude and making an angle of phi of t with respect to cos 2 pi fct line. The second term is a noise which is represented by the magnitude r of t and makes an angle of psi of t with respect to cos 2 pi fct line. Now, we have to do the vector addition of AC line and the r of t vector. So, if we do the vector addition, we get the resultant vector as shown here. This resultant vector makes an angle of theta of t with respect to cos 2 pi fct line, or it makes an angle of theta of t minus phi of t with respect to the signal vector. Here we have the noise vector. This noise vector makes an angle of psi of t minus phi of t with respect to the signal vector. The opposite side will be r of t sin psi of t minus phi of t. The adjacent side of the noise vector is r of t cos psi of t minus phi of t. Now, let us look at the angle of the resultant vector. Theta of t minus phi of t equal to tan inverse of the opposite side, that is r of t sin psi of t minus phi of t, divided by the adjacent side AC plus r of t cos psi of t minus phi of t. Therefore, theta of t is equal to phi of t plus tan inverse function. Assuming the noise vector too small compared with the signal vector, the resultant vector almost coincides with the signal vector. The opposite side will be negligible. Therefore, the denominator term we will have only AC term. Therefore, theta of t is equal to phi of t plus tan inverse of r of t sin psi of t minus phi of t divided by AC if the noise vector is much smaller than the signal vector. And again, tan theta is approximated to theta for theta smaller values. So, the frequency is nothing but the derivative of the angle which is given by the expression here. V of t equal to 1 by 2 pi derivative of theta of t, that is 1 by 2 pi derivative of theta of t is nothing but phi of t, where phi of t is 2 pi kf integration of m of t dt plus the other term derivative is 1 by 2 pi AC derivative of r of t sin psi of t minus phi of t. So, the differentiation and the integration will get cancelled, 2 pi gets cancelled, the terms left is just kf into m of t. And in the second term, let us represent by nd of t. Assuming carrier to noise ratio too high, the nd of t expression is simplified to just 1 by 2 pi AC d by dt of r of t sin psi of t. If we just observe the quadrature component of the narrowband noise, it is r of t sin psi of t. So, here the quadrature component is r of t sin psi of t. Here psi of t minus phi of t is approximated to psi of t if the signal component is much larger than the noise component. So, therefore, the quadrature component of the narrowband noise is r of t sin psi of t. Therefore, nd of t equal to 1 by 2 pi AC d by dt of nq of t. Now, let us look at the discriminator output V of t. It is finally equal to kf into m of t plus nd of t. In this, the signal component is kf into m of t, its power will be kf square into p. The noise component is nd of t. It is given by the expression 1 by 2 pi AC d by dt of nq of t. Now, let us look at the PSD of nd of t. So, before finding the PSD of nd of t, we should know the PSD of nq of t. So, now we know that from the property of the Fourier transforms, d by dt of x of t equal to j omega x of f. Therefore, Fourier transform of ND of t, which is equal to 1 by 2 pi AC j 2 pi f into Fourier transform of NQ of t. 2 pi gets cancelled, it is jf by AC Fourier transform of NQ of t. Therefore, PSD is SND of f is equal to square the function and the modulus, it will be f square by AC square PSD of NQ of t. Now, PSD of NQ of f, that is ND of t, we know from the earlier presentations given by the spectrum shown here. The PSD of ND of t is f square by AC square, that into SNQ of f. So, this SNQ of f spectrum, if we multiply by f square by AC square, we get the spectrum given here. This ND of f is then given to a low pass filter having a cutoff frequency of W hertz, which we get the spectrum as given here. If we find out the area under the curve, we get as N naught by AC square minus W2 plus W f square into df equal to this term. Therefore, the various SNRs are SNR at the channel, SNR at the output, and figure of merit is SNR at the output by SNR at the channel, which is equal to 3 kf square p divided by W square. The reference books, please refer to Simon Heikin, An Introduction to Analog and Digital Communication Systems, and the Simon Heikin Communication Systems. Thank you.